14.4. This is how I like to view a triple integral. We take our solid D and we break it up into infinitesimally small boxes. At each box we choose a representative point and evaluate the function there. Then we multiply that times the volume of that infinitesimally small box. We do that for every box and add up all the products and we get a triple integral. That, however, is not how we actually evaluate a triple integral. So let me show you in this video how to evaluate one. Suppose D is a solid such that x is between a and b, y is between two curves, and z is between two surfaces. Then this is the proper order of integration in that situation. And this is what the triple integral looks like. We're going to start with an example. Notice that our variable of integration for our inmost integral is z. Integrate and evaluate with respect to z. Then integrate and evaluate with respect to y. There's the integration and the evaluation. Lastly, integrate and evaluate with respect to x. And let's start a new example now. A solid box D is bounded by these 6 planes. The density of the box decreases linearly in the z direction. Find the mass of the box. Set up the triple integral. The big thing I want you to notice here is the setup. I set up in the same order z, y, and x, even though I really could in this particular case set it up in any order. But once you choose your order, make sure that your bounds match up with your order. So z goes first, and so my inmost integral, my bounds are between 0 and 1. And then y is in the middle, so make sure your middle integral is between 0 and 2, and then x is the outer, so make sure your outer bounds go between 0 and 3. After you do that, the integration is, for you, probably straightforward, but if you have any questions, let me know. You integrate and evaluate with respect to z, and then y, and then x. This order that I started the video with is really only one of 6 possible ways to set up the order of integration. It all depends on how the information is given to you. We do want to be flexible to all orders, and moreover, as in double integrals, sometimes we need to change the order of integration. So I want to do a problem where we actually change the order of integration. That's probably the hardest technique of all when it comes to triple integrals. This is probably the hardest thing you'll have to do. Alright, so we want to evaluate by changing the order of integration. Well, first of all, why should we? If you look at the integrand, we would have to first integrate with respect to x. We'd have sine of x to the 4th. Yuck. Well, if x shouldn't go first, who should? Y or z? Well, we don't know. We would really only be taking a educated guess. I'm going to guess y because I see y squared, and I know that the antiderivative of y squared is y to the 3 over 3. And that might help me with my x to the 4th. So who knows? But we will try it. But the first thing we want to do is to get a handle on our solid of integration. Let's first think about z. That's the outermost piece. Z is going to run between 0 and 4th root of pi. Given z, how does y vary? Y, given z, will vary between 0 and that value of z. What about x? The x-axis is coming straight out at you. What you're looking at is the shadow of the solid D onto the YZ plane. The actual solid is sitting above this plane. For a given point YZ in this plane, the values of x are going to run between y, that given value of y, and that given value of z. So x runs between the plane x equals z and x equals y. So you might want to take out the time right now to think about those two planes. Get out a couple of pieces of paper and play around and see if you can find those two planes and get a visual on them. Once you have done that, think of how for a given YZ in R, x varies between the plane x equals y and the plane x equals z. If in your mind you were able to think of a tetrahedron, my goodness, give yourself a big pat on the back. This is very hard to do. Okay, so by now you know that the solid is a tetrahedron. A tetrahedron is made up of 4 faces where each face is a plane. So I'd like you to look for the 4 planes of this tetrahedron. First, look at the plane y equals 0. Did you find y equals 0? Now look at the plane x equals z. That is the one I would say is facing you. Now look at the plane x equals y. If I were to describe that plane, I would say it was coming out at you. And now the plane z equals 4th root of pi. I would call that the roof of the tetrahedron. Once we have got at least a small handle on the solid, we want to think about changing our order of integration. I'm suggesting that we keep z on the outside. That means that our bounds for z stay the same. And I'm recommending that we switch the order of x and y. So given a value of z, just looking at values of z, how does x vary? To do that, look at the projection of the solid D onto the xz plane. For a given value of z, how does x vary? And for a given value of z, x will vary between 0 and z. Now for our inmost integral. The x equals z plane is running parallel to the y-axis, so it will not hinder how y varies. However, for a fixed value of x, the plane x equals y will restrict y. So for a given value of x and y, the variable y will start at 0 and run till it gets to the given value of x. So now we're ready to integrate and evaluate. Do that for the first integral. After you've done that, you can see the huge benefit of changing our order of integration. We still have sine of x to the 4th in the integrand, but now we have an x to the 3rd to go with it. Well, that's great because we can do a substitution now. Do the next integral and evaluate it. So the antiderivative of our second integral is 1 minus cosine z to the 4th once you've evaluated. And so now finish it up. And we get pi over 4.